All right, so lesson 29 here is on the second derivative test. We have done second derivatives, and we just briefly talked about the concept of acceleration when we were doing rectilinear motion. However, we haven't really done a whole lot with the second derivative yet, okay? So let's go back to kind of where we started and then talk about what this second derivative is used for, okay? So here we have our function f of x equals 6 over x squared plus 3, and we want to find the x values of which f double prime of x equals 0 or is undefined. So notice again here with the second derivative, we're going to be finding zeros and where it's undefined. Okay? So in this case here, don't forget that often if you have just a constant in the numerator, it's often easier to rewrite the function like you see here, 6 times x squared plus 3 to the negative 1, because I don't know about you, but I think doing the chain rule is a little easier than doing the quotient rule. So when I do f prime, I got to find the first derivative before I can do the second. It's going to be a negative 6 times x squared plus 3 to the negative 2. And then I've got to use the chain rule, so the derivative of x squared plus 3 is 2x. Okay? So, I simplify this a little bit here. I get a negative 12x times x squared plus 3 to the negative 2. Here, you kind of have a choice. Do I want to go ahead and write it as a quotient, use quotient rule, or am I going to use the product rule? Okay, I'm going to go ahead and use product rule. Okay, so f double prime, the derivative of the first half of that is just negative 12, so negative 12 times x squared plus 3 to the negative 2, plus the first term, which is just a negative 12x, times the derivative of the second part. So that's going to be negative 2 times x squared plus 3 to the negative third power times 2x. Okay? So some simplifying here would be really helpful. Alright, I'm going to go ahead and now write these as fractions. So negative 12 over x squared plus 3 squared. And I've got a double negative there, so it's plus. And I got 12x times 2 times 2x. So that's, and I get 48x squared over an x squared plus 3 cubed. Okay? So at this point, what I'd want to do, in order to solve for when this is equal to 0 or undefined, especially the equal to 0 part, I'm going to go ahead and get a common denominator. Because if I can get this as one fraction, then it equals 0 whenever the numerator is 0, and it's undefined whenever the denominator is 0. Okay, so I'm going to go ahead and do that here. And to get a common denominator, I just need to multiply by an x squared plus 3 over an x squared plus 3. So now that's going to be cubed. Okay? If I combine like terms now, distribute the negative 12, I'm going to have negative 12x squared plus 48x squared, which is 36x squared, minus 36, oh that's nice, over an x squared plus 3 cubed. Okay, so that is my second derivative.
Do you want us to distribute that to 36?
We can, and actually, now that we're at the end, okay, what's our last thing to do here? Well, set this equal to 0. So 36 times x squared minus 1 equals 0 when x equals plus or minus 1. When will this equal 0?
Plus minus.
Plus or minus what?
Oh, wait.
When x squared is negative 3, right?
Yeah.
Well, that's not going to be a real number, right?
Yeah.
So we don't care about that. It's always going to be defined for all real numbers. So our answer here, where is it? 0 or undefined at x equals plus or minus 1. Okay? It just said to find the x values, so we are done. These are not critical numbers. Those are just the first derivative, but they are useful, okay? And they're useful to deal with something that we call concavity. All right? Concavity is a little bit of an abstract concept. You can think of concavity if we're in the context of things moving around and stuff. You can think of concavity as our acceleration. Okay? But let's talk about what concavity is here and illustrate it here, and then we'll look at the second derivative test, which tells us how to determine concavity. It says, let f be differentiable on an open interval I. The graph of f is concave upward on I if f prime is increasing. So notice, before we were looking at the first derivative, and if it was positive, the function was increasing. Now we're looking at the second derivative. If the second derivative is positive, then the first derivative will be increasing. Okay?
So is that supposed to be the second derivative or the first? Because in the box it says the first.
Well, yes. F prime will be increasing if we're concave up.
Okay.
F prime will be decreasing if we are concave downward.
So the slope is your f prime. The derivative.
Yeah, if the slope, so you're thinking about the slope of the slope. As the slope is changing, how is it changing? Is it increasing? That means we're concave up. Is it decreasing? Then we're concave down. And these pictures here actually illustrate it pretty well. Okay? Notice here, this is concave upward because here my slope is negative, then at some point it turned to 0, and now it's positive, and now it's even more positive. It's gaining, the slope is actually increasing. Okay? So it's concave upward. Over here, you can see at this point, we actually had a positive slope. Somewhere in here, the slope equaled 0, and now it's negative, and now it's even steeper negative. The slope is decreasing. Okay, so we say that that is concave downward. All right? This is one thing that is really challenging for students to see sometimes. But what do you notice about all the tangent lines when we're concave upward?
They're below.
They all have the same.
What did you say?
They're below, like the graph.
Yeah, look, when we are concave upward, the tangent lines will always be underneath the function. You see that?
Would you have to find each individual tangent line for that function?
You wouldn't have to find equations, you could just sketch it. Okay? And then notice how we sketched over here where it's concave downward, all the tangent lines were on top of the function. Okay, so that's one easy way. If you're not sure, draw the tangent line and see. Now, where it's challenging is where you have a change in concavity. Because at that point, that's the point that we found up here. Okay? And I want to use this drawing up here. Notice we found the -1 and the +1. That's where concavity changed. And by the way, we can use a sign diagram for this as well. Okay? If I were to get a sign diagram, even if the problem didn't ask me for it, here, this is f double prime. If I plug in, say, a -2, the denominator is always going to be positive. Okay, because when you square it, it's positive, and a positive cubed is positive. So I look at the second derivative, if I plug in a -2, that's going to be 36 times 4 minus 36. That's positive. Okay? So that's why to the left of -1, notice I'm concave up here. Alright? And if I were to draw tangent lines, they would all be below the function. Okay? So this tells us a couple of things. It tells us f prime is increasing. F prime is increasing, and it tells us that f is concave up. All right? So you can kind of do a sign diagram like we did, but now it's telling us one thing about the first derivative, and that tells us something about the function as well. Okay?
So do you even need to find the second derivative, or can you just go up to the first derivative? Because wouldn't it work both ways?
Well, it depends if you know where the first derivative is increasing or decreasing, then yeah. So like if you had the graph of the first derivative, and you could see where the first derivative was increasing, yeah, that would tell you where it was going to be concave up.
But like, let's say your critical points for the first derivative were -1 and 1, and you still got increasing for the derivative, wouldn't that tell you it's concave upward?
Well, here's the thing, if it's a critical point on the first derivative, then it's not going to have a positive, well, I mean, it could have a positive. That actually, if it's a critical point at 1 or -1, and the second derivative equals 1 or -1, or equals 0 at 1 or -1, you'll have a point of inflection, which is a plateau point. If they're both 0 at the same point, you'll have a plateau point. We'll see that later. If the first derivative equals 0, but the second derivative does not, the second derivative can actually tell us whether it's a max or a min. And that's really what the second derivative test is going to tell us here in just a minute. Okay? But I want you to understand this concept of concavity. Alright, so if I were to continue the sign diagram, this would be negative and this would be positive. It would tell us that the first derivative was then decreasing and then increasing. And it would tell us that the original function between 1 and -1 was concave down, which we can actually see here. Okay, see all the tangent lines are above the function, it's concave down. And then again, it's concave up over here. So here it's concave up. Alright? So that's what concavity is. And notice here, like we just said, if the second derivative is positive in an interval, then the graph of f is concave up. If the second derivative is negative in an interval, then the graph of f is concave downward. Okay?
And if it's 0?
If it's 0, then we actually have a change in concavity. That's what we saw right here at -1 and 1.
Oh, is that equal to?
That's where the second derivative equaled 0. Okay? F double prime of -1 equaled 0. F double prime of 1 equaled 0. Okay? So you had a change from concave up to concave down. Just like with first derivative, we had a change from increasing to decreasing. Okay? So now, Again, all this is kind of preparation for the formal second derivative test that we're going to be learning, all right? We're just setting the groundwork here for the second derivative test in this section, okay? So here it says, determine the open interval in which this function is concave upward or concave downward. Now you can see the results right here, but let's actually take a look at how we would go about finding that. Okay, if I'm looking for concavity, that's a term that ought to automatically tell me I need to find the second derivative. Alright, so that's a connection that you need to make in your head. When I hear concavity or acceleration, either of those terms, I'm thinking second derivative. So let's find the first derivative first. Okay, so the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. This is where simplifying things can be really, really helpful before I try to take the second derivative. I'm going to actually factor the 2x out of the top. And notice what's left over. I have an x squared minus an x squared. That's kind of nice. So that's 0. X squared minus x squared. And I have a negative 4 minus 1. So that's a negative 5. So my numerator actually ends up just being a negative 10x. And this is over x squared minus 4 squared. Okay?
Would you do different to squares on the bottom? Or you can't because of the square thing?
I mean, you can. It would be x plus 2
Yeah.
squared and x minus 2 squared.
Would that give reason, would that make it undefined at plus or minus 2?
It would make it undefined at plus or minus 2, but we're actually not looking for critical values right now.
It's
We
only
want to get
first
second
I
derivative.
forgot
Yeah.
what I found.
Is it worth it to FOIL that out before doing the quotient rule again?
I would not, because remember, we want to look at where it's either 0 or undefined, so keeping it factored is going to be helpful. Okay, so now I do the second derivative. The derivative of the top is negative 10 times the x squared minus 4 squared minus the top times the derivative of the bottom, so that's 2 times x squared minus 4 to the first times 2x all over the bottom squared. So that's going to be x squared minus 4 to the fourth. That right there, guys, by the way, is where people mess up the quotient rule a lot. If it's already squared, they forget to square it again. So be careful with that. Okay? So then on my numerator, I see I have a negative 10, and I also have an x squared minus 4 in common. So I'm going to go ahead and factor that out. Negative 10 times x squared minus 4. And then I look at the leftovers. I've got another x squared minus 4 from the first part. Minus, let's see, I took out the negative 10, but there's an x left. I took this out. So there's an x, a 2, and a 2x. So that's going to be a 4x squared. So minus 4x squared. Those are all my leftovers after I factor.
You combine what you're in.
Yeah. And this is x squared minus 4 cubed. Or I'm sorry, to the fourth. But it's going to end up cubed because look, now I can cancel this out. Okay? I could cancel that out, and I get negative 10 times a negative 3x squared minus 4 all over x squared minus 4 cubed. Alright? Now, in this case, we weren't necessarily asked to simplify, but simplifying makes our ultimate goal a whole lot easier. Okay? The ultimate goal is to find where does this equal 0 and where is it undefined. Okay? So, I need to look at where the numerator equals 0. So that's going to be negative 3x squared minus 4 equals 0. So that means x squared would have to equal 4 over negative 3. So is that going to give us any results?
No.
Nope. Alright, so my derivative, my second derivative will actually never have a 0. But if I look at the bottom, where does that equal 0?
2. Yeah, plus or minus 2.
Yeah. So x is plus or minus 2. So I'm going to have a change in concavity, possibly, at plus or minus 2. How do I know for sure? I set up a sign diagram. So negative 2, positive 2, and I check my second derivative. Okay? If I were to plug in a negative 3 into my second derivative, negative 3 squared is positive. So I have now a negative minus 4. So that's going to be negative. Times a negative on top. So that's going to be a positive. If I do negative 3 squared, I have 9 minus 4, which is 5. Cubed is positive. So I have a positive over a positive. So it's positive. So that means F is concave up. Or sometimes we'll just draw a little thing like that. Okay? If I were to plug in 0 into my second derivative to be between negative 2 and 2, that would be 0 and that would be 0. I'd have negative 10 times negative 4 over a negative 4 cubed.
So big.
So it's positive divided by negative, which is negative. So this is concave down. And then if I plugged in a positive 3, it actually will end up being the same as when I did negative 3, because these were both squared, right? So it's going to end up positive and concave up again. So we're concave up, concave down, then concave up. And it asked us the open intervals, all right? So we should actually list those as intervals. It is concave up, for the intervals from negative infinity to negative 2, also from 2 to positive infinity. Okay? And then it's concave down on the interval from negative 2 to 2. All right?
It's accelerating from negative infinity to negative 2 and to negative infinity.
It is, we would say the acceleration is positive from negative infinity to negative 2. We don't know if it's speeding up or slowing down because we would have to compare the sign of our second derivative to the sign of our first derivative. So we'll be tying this all back together here pretty soon. But we addressed that just briefly before. Okay, so there's our results. Okay, concave up, concave down. And there we go. Any questions? Okay, cool.